33rd lecture, and we continue our discussion on power amplifiers, and if time permits we introduce the small signal model of the bipolar junction transistor, the BJT. In the last lecture, 32nd lecture, we had discussed the power amplifier with a transformer coupling. That is, what we had was, we had the usual transistor biasing circuit. Instead of a resistance in the collector, we had the transformer primary, and to the secondary is connected the load, actual load RL, which could be a loudspeaker, and then this goes to plus VCC, and the usual biasing circuit, there is a resistance R sub 2 and there is a resistance R sub 1. The input signal is applied between these 2 points. It's either a voltage source or a current source, either a voltage source or a current source. This is RE, this is a bypass capacitor. And we saw several advantages. The first was that the efficiency eta could be raised to 50% ideally. Eta could be raised to 50%. That happens because there is no DC loss of power in the collector resistance. Number 2, the load is isolated from DC. No DC flows through the load. That happens because of the transformer. What is the third advantage? Matching. It affords a means of matching by varying the transformer ratio N1 to N2. And what is its disadvantage, if any? It's costlier. Also, as you know, a transformer is bulky. It has to be iron cored if it is to be for audio frequencies, and therefore its weight increases, it becomes bigger in size. The rest of the circuit could be accommodated within a very small space, maybe within a matchbox or even smaller than that, but the transformer itself will occupy most of the space and will account for most of the weight. Nevertheless, to illustrate the design of a transformer coupled amplifier, we take a typical example in which the same specifications for the transistor hold as was used in the previous example of transformer less power amplifier, that is resistance load. Suppose we have a transistor in which the maximum VCE is 50 volt, the maximum power dissipation is 5 watt, and let us say beta mean is equal to 30, the same specifications as we had used in the previous example. Then obviously what you do is you look at the transistor characteristics, I sub C versus VCE characteristic. In these characteristics you draw the PD max line, that is a line in which VCE times I sub C is equal to 5 watt, alright. Then your VCE max is 50, so you prefer to go to the high voltages rather than high currents because the characteristics are more linear. So you mark a point 50 volt here, alright. Then obviously the maximum voltage swing can be 25 volts if the characteristics are ideal. So you mark the 25 volt point, and you know that for maximum power output your Q point must be on the PD max hyperbola, and therefore you go up and see where it meets. Obviously the current here shall be 0.2 amperes, and therefore your Q point is now determined, 25 volt and 0.2 amperes. Not only the Q point but the AC load is also determined. The AC load line shall be tangential to this and must pass through the 50 volt line. In other words, our AC, as we had calculated last time, shall be given by the slope of this line, which shall be 25 divided by 0.2 which is equal to 125 ohms. All right. Now, suppose in the transformer coupled amplifier, the actual load could be as low as, let us say, 5 ohm. Suppose this is 5 ohms. What you want here is 125 ohms, and therefore N1 is to N2 whole squared should be equal to 125 divided by 5. In other words, N1 is to N2 should be equal to 5:1. That means if the secondary has 10 turns, then the primary should have 50 turns. Okay. So the turns ratio of the transformer is determined. N1 is to N2 is equal to 5:1. Now, under this condition, what VCC shall be needed? Well, to determine VCC, you notice that the transformer primary, because of zero resistance, we assume it to be ideal, it does not drop any voltage, and therefore the only drop that shall occur shall be across R sub E. And you can set this drop almost arbitrarily, and as I said, 3 volts, 2 volts, these are typical figures. If we set this at 3 volts, let us say, if VE is set at 3 volts, then obviously RE needed shall be equal to, the current is 0.2 amperes, 0.2 plus 0.2 divided by beta, but since beta minimum is 30, we can ignore that term, and therefore what shall be RE? 15 ohms, 0.2 ampere flows, and we have assumed that VE equal to 3 volt, VE equal to 3 volt, and therefore RE is equal to 15 ohms. All right, do not be scared about the low value of the resistance. This is inevitable when your AC load is of the order of 125 ohms, a low resistance load. All resistances in this circuit are going to be low. All right, so RE is 15 ohms. Then what is VCC that is needed? 25 is given by the load line, 25 is the Q point, all right, that is, this will be the VCE plus the voltage drop across the emitter resistance. That means not 0.7, we are not going to the base circuit, it is still 25, VCC shall be equal to the drop in the transformer 0, the drop in the collector to emitter 25 plus 3 volts, and therefore VCC shall be 28 volt. All right. If you take nominal beta, equal to, let us say, 100, beta minimum is 30, if you take nominal beta equal to 100, then you can now calculate R1 and R2 in the usual manner. Okay. RB, that is the parallel combination of R1 and R2, shall now be beta min, that is 30, multiplied by RE, that is 15 divided by 10, and therefore RB should be equal to 45 ohms. All right. And you can calculate VBB from the requirement that VBE is 0.7, this voltage is 0.7, this is 3 volt, so this is 3.7. All right, VBB minus 3.7 shall be equal to IB times RB, from which you can determine RB, and therefore you can determine both R1 and R2. This calculation is routine and I shall not carry this out. But the next question is, how is the efficiency affected? What is the efficiency of this particular circuit? For that, of course, we shall have to look at the exact characteristics, and the characteristics of this transistor are depicted here. Now comes the question of practical considerations. All right, you see, this is the 125 ohm line, 25 volt, 0.2 ampere, this is the Q point, and these are the actual characteristics, the blue lines. All right. Now, if you look at the actual characteristics, you notice that the AC load line, the red line, cannot quite go to 50 because it crosses the IB equal to 0 milliampere line, and therefore this must be your maximum VCE. You cannot go to 50, you can go only up to about 47. All right. In a similar manner, you notice that the curve cannot go right up to this point, because the saturation part of the characteristic is to be exceeded. Therefore, you notice where does it cut? It cuts at IB equal to 8 milliamperes. So this is the maximum I sub B that can be allowed. Small I sub B can range from 0 to 8 milliampere. And because of saturation, the voltage cannot go below 3 volts. And therefore, V max is 47 and V min is 3 volt. All right. And therefore, the root mean squared value of the output signal can be 47 minus 3, that is 44, divided by 2, that is the peak value, 22, and the root mean squared value shall be 22 divided by root 2. All right. Is that clear? We are not taking the current into consideration. Why? Because we are not going to the maximum possible current swing. All right. So, my root mean squared value of the load voltage V sub C shall be 22 divided by root 2. Do all of you understand why it is 22 by root 2? Maximum V minus minimum divided by 2 is the peak value. Peak value divided by root 2 is this, and therefore, the output power P0 shall be Vc squared divided by RAC. So, 22 by root 2 whole squared divided by RAC, which has already been determined to be 125 ohms, and this calculates out to 1.94 watts. All right. This is the output power. The input power P sub C, input power P sub C, or let's call it P sub I, capital P sub capital I. The input power is simply VCC multiplied by whatever current is drawn from the battery. Well, from the battery is drawn a current for the collector circuit and also for the base circuit, but the base circuit current is much smaller compared to the collector, and therefore is simply multiplied by I sub C, which will be equal to 28 multiplied by, what is I sub C? 0.2. This is equal to 5.6 watt. Agreed? Does that bother you? Where is the PD max, the maximum dissipation that the transistor can tolerate is 5 watt. So where does this 0.6 watt, where does it go? It goes into RE. It is not the dissipation in the collector, it is the dissipation in the emitter resistor, and therefore the efficiency eta would be 1.94, the load power, divided by the power that is supplied by the battery multiplied by 100%, and this calculates out to approximately 35%. The theoretical maximum is 50, what we can achieve is approximately 35%, and this is a fact of life. All right. The design has to be very carefully done by looking at the transistor characteristics. For power amplifiers, transistor characteristics are a must if you wish to keep the distortion to within reasonable limits. Now, if we go back to this operation, to this transistor characteristics once more, you notice that if we choose our Q point here, then for the input current, what is the input current? The base current? If the base current is 4 milliampere. Now, suppose the base current, the AC input is such that the base current varies from, let's say, 2 milliampere to 6 milliampere. Then obviously, for the total cycle of the base current will be 4 milliampere plus an AC of peak value 2 milliampere. Suppose it is so. Then for the total duration of the base current cycle, the collector current flows. The collector current flows for all times, all right. On the other hand, if we had chosen our Q point, let's say somewhere here, all right, then the collector current would have flown only for a part of the base current cycle, or maybe the Q point is here. If here we apply, let's say, a 2 milliampere peak AC, then for the positive half cycle there is no point, there is no problem, but for the negative half cycle you shall have a problem. Now if the peak value is more than 2 milliampere, let's say 4 milliampere, then obviously for the positive half cycle the current shall flow, but for the negative half cycle only up to 0 milliampere, only this much will flow. In other words, there shall be distortion. It is as if you take a pair of scissors and cut the negative half cycle, all right. Suppose we go to an extreme. Suppose we put our Q point, let's consider this. Consider ideal characteristics. Ideal characteristics would be like this and suppose your load line is this. As I said, there are many choices of Q point. Q point could be here, could be somewhere here, and you could arrange so that for all times the collector current flows. But suppose Q point is here, then obviously it is only the positive half cycles of the base current which will cause a collector current to flow. For the negative half cycle the collector current shall not flow, because I sub B cannot go negative, all right. This is the maximum. The current is not injected, and therefore the collector current has no obligation to flow. The collector current shall not flow. In other words, if the Q point is here, let's say QB, then it acts more like a rectifier. Isn't that right? It only takes the positive half cycles. Now how is this achieved? This is achieved by biasing the base, by choosing R1, R2 and R1 in such a manner that VBB is just 0.7 volt. Agreed? It is so arranged that VBB is just 0.7, that is, in the characteristics the transistor, the base emitter junction is biased exactly at 0.7, so that if the base voltage is less than 0.7 the transistor does not conduct, all right. This operation, this Q point is called the class B operation, class B, in which the current in the collector flows for only 1/2 cycle of the base current, whereas if it flows for the total cycle then it is called class A operation, class A. In class A operation the collector current flows throughout the duration of the base current cycle. In class B operation the collector current flows only for half cycle of operation. If it is in between half and full, then it is called class AB. It is neither class A nor class B, it is somewhere in between, class AB. There can be intermediate class AB. Now suppose you go to the other extreme, that is, you take a transistor let's look at the base circuit only. Suppose instead of a positive battery here, instead of positive VBB, you connect a negative VBB, all right. Then you see, if you apply through a capacitor, if you apply an input signal here which varies like this, all right, then the transistor will conduct only when Vi exceeds VBB, isn't that right, by at least 0.7 volt, otherwise the transistor will not conduct, and therefore what will happen is the collectors, in the collector circuit only a part of the positive half cycle shall make the only during a part of the positive half cycle the collector current shall flow. In other words, if I continue this then what you will get is pulses like this in the collector. Now you might ask, this is obviously a very highly distorted collector waveform. What is the use? The use is the following. In class B operation, in class B only the positive half cycles allow the collector current to flow. Then what is done is 2 transistors are used in a configuration known as the push-pull configuration, push-pull. The basic idea is that one of the transistors conducts during the positive half cycle, the second one conducts during the negative half cycle. And the outputs are so combined that there is no distortion. Alright. This is the advantage of class B. Now what is the advantage? Why should one do that? The advantage, as you see, if this is the Q point, then what is the quiescent collector current? 0. Isn't that right? Without the signal, collector current doesn't flow at all, and therefore power dissipation in the transistor is minimized. Alright, power dissipation in the transistor is reduced drastically, and therefore the efficiency improves. The efficiency improves. As we will see, the efficiency can be as much as 78.5%. Let's remember efficiency. Class A with a resistance load, maximum efficiency is 25%. Class A with a transformer coupling, maximum efficiency is 50%. Class B with push-pull operation, maximum efficiency can go to 78.5%. And class C, the efficiency can go further up. It can go to as much as 85% or so. Alright, 85%. Now, the problem of distortion, as you see in class B operation, as I said, 2 transistors are used. One takes care of positive half cycle, the other of the negative half cycle, and the 2 outputs are so combined that a full cycle of the output is obtained. So there is no distortion. In class C, this is not possible, because even a half cycle is not obtained. So what is done is, from these pulses, little pulses, you know that such pulses can be decomposed by Fourier analysis into its fundamental and harmonics. What is done is, these pulses of current are passed through a tuned circuit, a parallel resonance circuit, which is resonant at the fundamental frequency. Alright, resonant at the fundamental frequency, which means that at the fundamental frequency the impedance of this is very high. At all other frequencies the impedance is low. So the voltage that will be developed across this tuned circuit will be mostly that of the fundamental frequency, and that is how a sinusoid is restored. Now this is the operation, class C is the operation that is used in all transmitters, radio transmitters, because of the high efficiency. You see, in radio transmitters, if you have a 100 kilowatt transmitter, then cooling 100 kilowatt, the power dissipation in the transistor shall be, let's say, 50 kilowatt. Cooling 50 kilowatt of heat is a very elaborate job. So higher the efficiency, the lower will be the effort in cooling the station. Alright, very elaborate arrangements have to be made, and therefore class C operation is restored to in radio transmitters. And in any case, you transmit only a narrow band of frequencies centered around a particular frequency. Delhi B, for example, 1000 kilohertz, and the speech band around it, and therefore all you have to do is to make a tuned circuit of 1000 kilohertz. Alright, so this is the operation of class A, class B, and class C. We shall not have occasion to look at class C, but class A, class B definitely we are going to look at. This is a pictorial representation of the three classes of operation. You see, this is a plot of I sub C, collector current, versus I sub B, the base current, and this curve is linear. For equal increments of base current, you get equal increments of collector current, provided the base current is positive. We are talking of what kind of transistor? NPN. For PNP it is the other way around, base current has to be negative, it has to go out of the base. Alright. So, if this is the Q point, then obviously if the base current varies like this, the collector current varies like this. So, the collector current flows for the complete cycle. If the Q point is shifted here, then it is only this part of the base current which makes the collector current flow. So, the collector current is simply half sinusoid. On the other hand, if the Q point is shifted somewhere here, that is, the base is negatively biased, so that the signal has to rise above this limit to make the transistor conduct, then you shall get only parts of the positive half cycles, and this is the class C operation. These three terms should be remembered. What we have discussed so far is class A only. Now, let us look at a typical class B operation. As I said, in class B you use two transistors, okay. You use two transistors like this and in the base circuit you feed the signal through a transformer. This is your signal to be amplified, Vi, alright, and the base bias is provided by a VBB like this. This VBB I have shown it schematically, but it is obviously derived from VCC through a potential divider. I have simplified this circuit by showing another additional battery, but actually VBB is derived from VCC, only one power supply, by an appropriate potentiometric division of voltage. VBB, if it is to be class B operation, it has to be just on the verge of conduction, that is about 0.7 volt if it is silicon. Now, in the collector circuit, you see there are two transistors, Q1 and Q2. In the collector circuit, the two collectors are connected through a transformer, the center tap of which is connected to this point, and the battery VCC is connected here, VCC, alright, and the load is the secondary of the transformer, is in the secondary of the transformer. Let us call the load as RL. This is the circuit. Do you understand the circuit? There are two transistors needed, one is the input and the other is the output. Both transistors operate under class B condition, that is, normally it does not conduct. If there is a signal, in the absence of a signal there is no collector current. Let me show the directions of the collector currents. This is I sub C1 and this is I sub C2. So, if you see I sub C1 and I sub C2 flow in opposite directions in the transformer, alright. That means if it tries to create a flux in the positive direction, this tries to create a flux in the negative direction. Is that okay? Is that clear? And the battery has to give out IC1 plus IC2 by KCL. By KCL, the battery has to deliver I sub C1 plus I sub C2. Now, let us look at what these I sub C1 and I sub C2 consist of. You see, when the AC is such that this is positive and this is negative, when the signal is such that the upper terminal is positive with respect to the lower terminal, obviously Q1 shall conduct, Q2 shall not conduct, all right. When this point is positive with respect to the lower point, Q1 shall conduct, not Q2, because Q2 base is then negatively biased, all right. All right. So I sub C1 flows, IC2 does not flow. How much? For how long does IC1 flow? Only for half a cycle, only for half a cycle. Therefore, if you plot IC1, it would be like this. IC1 will be pulses like this, half cycles. If you plot versus omega t 0 pi, yes, how much is this? 2 pi, then 3 pi and so on, all right. Now, when the polarities are reversed, that is, this becomes positive with respect to this point, then the opposite thing happens. What happens is Q2 conducts, Q1 does not conduct. If Q2 conducts, I sub C2 flows. Now, I sub C2 obviously shall also be like this, where it will start from pi and it will go to, yes, 2 pi, then this will be 3 pi and this will be 4 pi and so on. This is I sub C2. This is too small. Can you say this? Okay. And the current that flows in the transformer primary obviously is IC1 minus IC2. Agreed? Because they flow in the opposite directions. Now, if you take IC1 minus IC2, what do you get? You simply get the full wave here, all right? IC1 minus IC2. And therefore, what flows to the primary over a certain duration of time is the complete cycle. And therefore, in the secondary across RL, you also get the complete sinusoid. And there is no distortion, all right. But the advantage is, what is the advantage? That it's only one of the transistors which conducts. Normally without signal there is no power dissipation, and therefore the efficiency should be high, all right. Let's look at what can be the ideal efficiency. Is the operation clear? Is there any question? No. Is there any question? No. What is the input power? Input power obviously is VCC. Let's look at this once more. Input power, what does the battery give out? IC1 plus IC2. Now, IC1 plus IC2 obviously is the full rectified sine. Isn't that right? And what is the DC that is drawn from the battery? The average value of this? If this is I max, then what is the average value? 2 by pi multiplied by I max. And therefore it is VCC times I sub C, where I sub C is I max divided by pi. No, twice I max by pi. So this is equal to twice VCC I max divided by pi. What is the relation between VCC and Vmax? What is the relation between VCC and Vmax? If you look at the circuit again, is there any drop here in the transformer? No. And therefore VCC must be the Q point. VCC must be the Q point. Agreed? The load line must be, the DC load line is a vertical load line. Agreed? And therefore, is this point clear? VCC is equal to Vmax? No. It's not clear. All right. You recall this. In the characteristic, if this is the AC load line, then the middle point is the Q point. This represents minus 1 by RAC. This is the Q point, all right. Now, what is this? What is the relation between this point and VCC? This must be the VCC, because the DC resistance of the transformer primary is 0, and therefore the DC load line must be vertical. Wherever the DC load line cuts is VCC, all right. So, what is the maximum possible swing? Obviously, the collector voltage can swing from 0 to twice VCC, and therefore the peak value of the AC, that is V max, shall be equal to VCC, all right. And therefore my input power is twice V max I max divided by pi, all right, twice V max I max divided by pi. This is the input power, P sub I equal to twice V max I max divided by pi. And what is the output power? Output power shall be the root mean squared values, the product of the root mean squared values of load voltage and load current. So, it would be V max divided by root 2 and I max divided by root 2. This is my P0, and therefore the efficiency is, if you divide this by this, you can easily see that this is equal to pi by 4. Root 2 multiplied by root 2 is 2, and this 2 pi by 4, which is how much? Approximately 78.5%. This is the maximum efficiency that you can get from class B operation. And most of the stereo amplifiers and public address system amplifiers that you see operate under class B conditions, because efficiency is important there. One of the any question at this point? One of the greatest disadvantages of the power amplifier class B operation is that the cost increases due to the two transformers. One is required at the input, the other at the output. Two transformers are needed. Of course, the input transformer is a much smaller transformer. Why? Because it does not have to dissipate. The input signal will be usually a very small signal, all right. The question is, can we reduce that cost? Can we avoid these two transformers? Yes, indeed it is possible only in semiconductor devices. This is something new as far as semiconductor devices are concerned. Its predecessor, the electron tube, did not have anything like this, because in electron tubes we did not have complementary transistors. In semiconductor devices we can have NPN and PNP transistors. By making a combination of two such transistors, instead of using two NPN or two PNP in a class B push-pull amplifier, if you make a combination of NPN and PNP, then you can avoid the transformer. Let me draw the circuit first, then I will explain. The circuit uses what is known as, well, you have known common emitter amplifier. Circuit uses common collector stages, that is, each of these stages, NPN and PNP stage, which are connected in a push-pull configuration, they are, instead of CE, they are CC. That means the collector is common between input and output. While the actual circuit is like this. For each transistor, I am showing an NPN first, then I will show the PNP. This is connected directly to VCC. The collector is connected directly to VCC. Then as far as AC is concerned, this collector is grounded. Agreed? As far as AC is concerned, collector is grounded, and this is why the name common collector. Then the input circuit, the usual circuit, that is, you have R1 and R2. The load now, the load is not in the collector, because collector is common. The load is in the emitter. this is the load, and the output voltage is taken from here. The input is applied between this point and this point. This is a typical circuit for a common collector amplifier. Now, if you take the voltage between B and G, if we call this as ground, if you take the voltage between B and G, V, B, G is the DC part of this voltage, and there is an AC part also, let us say small v sub small b small g. This is the DC part and this is the AC part. Alright. This voltage has two components. One is prescribed by VCC, R1 and R2, and the other is the voltage that comes from the input signal. Alright. It is important that you understand what I am writing. The total voltage here is the sum of an AC part and a DC part. Now, obviously this must be equal to the VBE, which is DC, which is a constant when the diode is conducting, plus VE. VE has the voltage across RL has an AC part as well as a DC part. So, VE plus small VE. Is that clear? And if the transistor is working in the linear region of its operation, then obviously the AC part on the left hand side must be equal to the AC part on the right hand side. That means whatever you apply here must have come here. In other words, the voltage at the emitter obviously then follows the voltage between the base and ground. Is the point clear? It is the AC part or the signal part, not the DC. As far as DC is considered, VBG is equal to VBE plus VE, alright. In absence of a signal, this is what will happen. In the presence of a signal, whatever you apply between B and G shall now appear across RL. And therefore, this circuit is also given the name emitter follower, which means that the emitter voltage follows the base voltage. So, what is the voltage gain? 1. Then why should one use this circuit? There is a current gain. If the base current is IB, the emitter current shall be beta times IB. Now, if the voltages are equal, input voltage is equal to output voltage, but the output current is beta times the input current, obviously there is power gain, alright, and therefore this circuit can be used to advantage. This circuit is known as an emitter follower. Now, let us look at the power amplifier, transformerless power amplifier using complementary transistors. The total circuit is known as complementary symmetry circuit. Complementary symmetry circuit. Now, try to draw with me. We have plus VCC. Let us draw the NPN transistor first. You see there is nothing in the collector because it is to be an emitter follower, and the emitter is then connected to an RL as you saw earlier and the output is taken here, alright. The base is biased in the usual manner, that is you have an R2 and then an R1. I will not complete this circuit here because I have to draw the other transistor also. Alright. Then the other transistor instead of NPN, let me show it in a different color, it is PNP, and therefore the emitter goes in, the collector comes out. And to what kind of a supply should this go? Obviously to a negative supply, so minus VCC. You could have a single supply, this is the positive terminal and this is the negative terminal, or you could have two supplies, alright. There are supplies available, plus 12, 0, minus 12, alright. So this is the condition, and then the usual biasing circuit. The biasing circuit is again the same, R1, R2. Obviously, in order that the push-pull circuit works, the two transistors must have identical characteristics. So Q1 and Q2 are two identical transistors, except that they are complementary symmetry. That is, one is a PNP, one is an NPN and the other is PNP. Now, where should this go? These two R1s are connected, and the input is applied between this point and ground. The output is taken from here to ground. Let us see what happens when when you connect an AC source, let's say here. When you connect a signal source here, when this terminal is positive with respect to this terminal, then current flows like this. The current flows through the PNP transistor. So the PNP transistor conducts, I am sorry, not PNP, NPN transistor conducts, and it allows a current to flow like this. Is that clear? Why doesn't the current flow in this direction? Because Q2 does not conduct. Is the point clear? R1 and R2 are so selected that the bases are just on the verge of conduction. So as soon as this terminal is positive, a current flows like this through the transistor Q1 to the load RL. Alright. On the other hand, when it goes negative, when this becomes positive and this becomes negative, Q2 conducts, that is, the current now comes from the base of Q2, right? It is a PNP transistor, current comes from the base of Q2 and flows like this. And therefore, what happens is the current comes into the emitter and flows like this. Agreed? And therefore, what does the load see? Load is never deprived of any current. It gets current during the positive half cycle from Q1, it gets current during the negative half cycle from Q2, and it gets in the correct direction, and therefore the voltage across RL is simply the full sine wave. And this circuit is the most popular power amplifier circuit. It is called the complementary symmetry power amplifier circuit. Complementary symmetry, you can give other adjectives. Class B, push-pull circuit. The complementary symmetry required, you wanted to avoid transformers, right? And therefore, the collectors have now been declared as dead. They are connected to ground. Collectors. You take the output across the emitter, and this is why I had to introduce the emitter follower circuit. All right. This, as I said, is the most popular circuit. In the next class, that is Friday is 1 hour, okay, 4 to 5. In the next class, we will start small signal modeling of the bipolar junction transistor.